So today's parallel meeting, we were going to talk about how the LLVM backend, and I guess the job server a little bit. Is that right? And I think Alex is going to be the main one to do the talking.
Yeah, so I wrote up a document just kind of an overview of what the parallelism is and kind of where it is in the job server specifically. I don't mind going over any of the various pieces, but so I don't mind like diving into one particular one, but we can also just start with the job server and see where it goes from there.
Yeah, I was sharing your document here. I'm happy to go in any order. I would basically I think, correct me if I'm wrong, but it seems like our impression is that overall the sequential overhead is not too bad. It can always get better, but it's not that bad. But the gains we're seeing are not as high as we would like. And we think that this may have something to do with the interaction of job servers and LLVM and so forth. Does that sound correct?
Maybe? Kind of. Not the last time that I benchmarked the current, what we exactly have in tree right now, I do think a lot of the performance is related to the job server, but I don't think it's related to LLVM's integration at all. I believe that there's this is where a little while ago we were talking about maybe reworking, maybe Rustc doesn't want to use Rayon, maybe it just wants to use parallel for loops in a few places. And so that is where, like right now, I think the Rayon integration has very, very fine-grained where it acquires and releases a job server token, and that causes a huge amount of traffic to the kernel, and that's one of the main reasons I think that we're having sequential slowdown. So it's not actually explicitly related, as far as I know, to the current job server integration of the LLVM backend.
Okay. Well, why don't we start in whatever order you think? I still feel like it'd be good to cover both those things if we can, so whatever order you think is best, but that makes sense what you're saying. And it's actually encouraging, I guess, because it suggests we might be able to get better performance without as much restructuring.
And so I do think it's worthwhile to talk a little bit about what we want to do with the CodeGen backend going forward, because I do think there's going to be some big simplifications we can have with a fully parallel compiler. So yeah, let's just go through this. So do you want me to just kind of basically I'm fine doing whatever's easiest. I can just go down this doc and kind of give the high level points, and then we can kind of drill into questions as they come up.
Yeah, let's do that.
All right. So the number one thing to do here is actually, if you want to scroll down and click on the graph, that little picture looking thing, that's going to be the easiest thing to take a look at. Yeah. So I guess you can't really see my cursor, but anyway, so the parallelism on the back end all has to do with.
I didn't mean to do that.
I'll reopen
it. But although you could also share your window if you want.
Oh, you're right. I can.
It makes more sense.
Share. There we go. All right. Can you see my screen?
Yes.
Yes.
All right. I'm going to go bring up a blown up portion of the picture. All right. This is perfect. Okay. So all of the parallelism that we get is not in the compiler itself, but rather through LLVM. So all the CodeGen, what it has to do is it needs to take a bunch of the Rustc data structures like mir, translate them to LLVM IR, and then once we get to LLVM IR, then we have to optimize it and then CodeGen it. The translation phase has to be serial because it uses the type context, and that just inherently is single-threaded right now. So this big bar right here we see at the top, this is translation. This is the main thread performing translation, and then kind of as soon as we have an LLVM module ready to go, each LLVM module is completely independent from all the others in terms of LLVM data structures, and so that is safe to send across threads. And so we basically create an LLVM module, send it to some other thread, and then some other thread goes off and codegens it. So we have this kind of you can see this this stair effect going on here, and what that means is that the main thread is serially translating a module, forking off to a thread, and then as soon as it finishes this module, it translates a little bit more, then it forks it off to this thread. And so we can kind of see that the stair part is kind of what the main thread has to do to serially produce this work. And we can see that while one thread is optimizing, the main thread is continuing to translate more and kind of fork more work off later. And so this graph is particularly a very nice stair in the sense that this was a many core machine with 16 CodeGen units, and so we never actually had threads picking up work from other places, except for kind of like this one thread right here. But in any case, that's the main phase of parallelism, where so the main thread will translate stuff, send it over to other threads, and then they will optimize. The optimization even happens in debug mode. It handles things like inline always. It's very, very fast, things like that. And then what we're looking at here is actually a optimized build. And so there's this kind of wall at this portion. And this represents the thin LTO passes. So as soon as every single cogen unit from the left side is optimized initially, this one from thread 2 is the very last one, so it finishes right about here. That translates to this. We do a tiny amount of work to do thin LTO analysis, and then we, as you can see, we fork off a bunch of LTO stuff to actually happen later on. And so that's where all the parallelism comes from. So this is sort of like at a high level what the parallelism in Rustc currently looks like, which is like the stair step of like we're creating a bunch of parallelism, and then we lose it all, and then we regain it all for a little bit, and we have thin LTO. Making sense so far?
Yeah, I have a question. How often have you looked at these sort of graphs? I'm a little bit, I think it's very interesting how uneven, how there's like a few modules that are taking a long, it's totally orthogonal to what we're doing, but it is interesting. There are a few that are taking a really long time.
Yes.
Makes me wonder if we should like, sort the order with which we create them. To try to get those out of the way fast first.
This is there was like a really crappy format for viewing these, crappy in the sense of it was not nearly as fancy as the current one. So this is very, very recent from the self-profiling work, and it's made it so nice to view these kinds of graphs. So the answer is no, I've barely been looking at these, and the other answer is yes. As soon as you look at them, you're like, we can do a lot better. And so that's the only section I wrote here about cogen units, which is that for parallelism, this isn't too interesting, but the main thing is what you were just saying of like, we're not doing a great job of balancing these things out. And it turns out there's a pull request which basically is just kind of rejiggering things, where it turns out we were partitioning to make, we want to make it kind of as even as possible, but then we were inlining afterwards, which drastically changes. So this is basically saying let's inline and then partition. So anyway, that's,
I remember us
right?
saying frequently we would tune this, and we, as far as I know, never really did. Probably partly because we didn't have the ability to visualize it. But, yeah.
I believe that's correct. And yeah, having this is like, this is what we need to visualize it, because it's so easy to see here. You have these like two modules that are doing nothing. Oh, oops, oh, crap. I did the same thing you did. Can I move this like bar to the other side of my screen?
Yeah, you can just drag the bar around.
Oh, there we go. Okay. So you have like these, this is obviously much larger than it needs to be, and it's preventing like a bunch of idle work. But yes, anyway. So yeah, that is known. I think we do need to work on it, but it is somewhat orthogonal to this work in general. Any other questions so far?
And to be clear, like the stair step, the purple bars, all of that is not sort of inside Rustc, right? That's LLVM code entirely.
So this bar at the top is the main thread actually translating to LLVM. So that's mostly in Rustc because we are manufacturing LLVM IR. But yes, every single other one is predominantly, we just called LLVM and said run your optimization passes, and that's like the entire thing. There's like little tiny pieces where, no, it is. It's just all LLVM.
Right.
And this is like, the LLVM is where we are actually executing LLVM on multiple threads. All right.
And there's no like further partitioning we could do, in terms of LLVM. We're sort of as parallel as LLVM allows us to be, right?
As far as I know, yes. I think there's been some efforts a long, long time ago to parallelize within a module, but I'm not really sure they ever got off the ground or landed in tree. Now that could be wrong. It's been years since I took a look at this, but I'm relatively certain that because this would be one of the #1 things that Clang would want to enable. So I believe that if it was there, they're like a bunch of fanfare about it. So I think because Clang hasn't said anything, I highly doubt LLVM can parallelize within a module, and it's only, we have to parallelize at the module level, which is very coarse. It's just an object. It's like the object file level.
Yeah, I think that's right. Not that I know any more than you.
But all right, so kind of an overview of what can and cannot be parallelized. So we have these 5 steps, which the first one is we have to actually split cogen units in Rustc. We just have to figure out what's where. That's kind of hard to parallelize. You can make the query parallel, but you can't parallelize it too much. I mean, the actual translation.
It's worth noting that the current parallel compiler does indeed parallelize part of this stuff.
It will get it from like kind of the inherent parallelism of queries. If we do the parallelization at the query level, if we do parallelization with for loops,
it does it. It does it within the query because of the Rayon
but
integration.
Are we for sure keeping that model?
No, just saying the current code does.
Yes.
It might be an argument in favor of, well, maybe I was pushing, like I was kind of one of the people saying maybe we should dump this, and seeing that made me reconsider that maybe if it's not too hard, or we should think about if we can keep some of it.
That is true, and I haven't done a huge amount of profiling, but it's a non-trivial amount of time in the compiler. It's not massive, just the splitting things up, but it's not tiny either. Like it's not just inconsequential. But the next part, which is the most interesting one, is where we actually translate to LLVM. So we're translating a bunch of mirror to LLVM-IR. That today is not parallel. That actually can become parallel once we get parallel like the whole parallel compiler. And so that's the number one major simplification of the CodeGen backend, is we can just translate everything in parallel all at once. So we don't have to have this like coordination between the main thread, the worker threads, and all that. That's like a really big thing I wanted to call out. And this is like today it's sequential, but it can be parallelized. CodeGen, that's already parallel. We don't have to worry about that. FinLTO is by definition serial, so we just can't do anything about that. And then the actual translation after FinLTO is already completely parallelized. The major win is translation can become parallel, and we can't land that today until we actually turn for the parallel compiler on by default.
Are you suggesting? Well, I'm gonna let you keep going, and I'll ask more questions.
Okay. All right. So I'm not going to go too much into this. At the beginning, there's like this weird detail. We have like, so everything in the compiler is controlled via a coordination thread that is not the main thread. And the coordination thread is the one that decides everything. It'll tell the main thread CodeGen a module. It'll actually spin off a thread to go work on LLVM. It'll be the one doing thinLTO passes, or sending that to a thread to do thinLTO passes. And so it is a very long comment. I'll click on it. This is a very, very, very long comment that goes and goes. And so actually, I read that recently, and it is still pretty accurate and pretty up to date in terms of what the coordinator thread does. But this is largely implementation detail, and I expect this to almost entirely go away once we get a parallel compiler, because we just won't need this crazy like moving between the main thread and back. So I'm mostly gloss over that. But does anyone want to ask?
Well,
about that specifically?
That's sort of related to my question, I think. The one thing I remember distinctly from when we first introduced this parallel stuff, especially with incremental, is that we were initially killing our peak memory usage because we were translating to lots of CodeGen units and then running them all in parallel, and that was killing us. And I think you and MW kind of did this work to like sort of don't do more than n at a time, reduce the peak memory usage basically, as well as starting as soon as you can, which is good. And I'm a little bit nervous that if we just made it so that each query takes a CodeGen unit and like runs it, I guess we kind of get some of that for free. Now that I think about it, we sort of get some of that because Rayon already doesn't run more than like n things in parallel, or whatever our underlying, doesn't have to be Rayon, but we're going to have a fixed number of worker threads, and that'll already kind of limit the total amount of concurrent work. So maybe that is a moot point. But
yes, and so I scrolled down a bit. This is a section that I wrote specifically on this, and you're definitely right. So it used to be like that stair step didn't used to happen. We used to, when we first had parallel compilation or parallel CodeGen, we translated everything serially, and then in parallel we did everything in parallel. So that meant our peak memory usage was literally every single LLVM module in memory, the biggest it's ever going to be because it's unoptimized IR, plus the type context and everything related to that. So that was what killed us, and we needed to fix that. And I actually tracked it down. It was a somewhat innocuous PR, which doesn't sound like it's tackling exactly this, but it was when we introduced that stair-stepping effect. And the explicit purpose of that was that we want to make sure we don't hold literally everything in memory all at once. And so we still hold. I know so I think that one of the main things is like we want to drop the type context as soon as possible after we translate everything. We also want to, but on the other hand, we do actually have every single LLVM module in memory at once when we do with FinLTO. And so if I remember, we have to talk to MW because he might know for sure. He was definitely the one that was investigating this, and I'm pretty sure it came from Firefox. But I think it was incremental. Or an incremental, you can have hundreds of thousands of object files, and having all those in memory all at once was the major killer thing when we had
Yes,
to reduce that.
I think that's right.
And
There was a
so in
lot of
that sense, the
duplication
thin
between
LTO,
them also.
yes, and so the thin LTO there is not nearly as it doesn't matter nearly as much because we don't retain things in memory, and so I really like this is like the pseudocode for kind of what I expect the CodeGen backend to look like eventually is like we'll have some query to get the CodeGen units, but this is sort of like what you were saying of the inherent limitation of the job server and Rayon, I believe will make sure that we cannot have all this in memory all at once. And as I was writing this, I realized I think the main thing is we need to drop the type context as soon as possible. But like this is an example of like thin LTO, but if you didn't do this, we would just cut out this step in general, and so we would like memory would be the entire LLVM module would be dropped as soon as it could, like once we actually create the object file. And so like this is definitely something we need to we must avoid. Like this is a problem we must continue to deal with. But I'm pretty sure that we can largely let the job server limitations of like just inherent parallelism guide us as opposed to having this like weird heuristics for who's doing what when, because that's all based on the fact that we have to, the main thread is the only thread that can translate things, whereas if we otherwise said that every thread just picks up a module, takes it all the way to completion, and then starts the next one, that model is just inherently more naturally self-limiting because it's like you started it from front to back, so no one's producing everything all at once. There's only like if you said -J10, there's only at most 10 LLVM modules in the system at any one point in time.
Do you remember the query structure? Like here you wrote translate to LLVM and optimize as separate steps, but I imagine you might actually want them to be like one query basically that just says produce the end result of this CGU, right? Which is do optimizations.
Well, it's a little more. It's difficult because if you're not optimizing, so if you're not doing thin LTO, then everything can be one parallel for loop because you just want to translate and then CodeGen. If you are doing thin LTO, you have a synchronization point where you have to optimize once where you don't do CodeGen, and then you do some stuff, and then you optimize again in CodeGen after that. And so whether or not you have thin LTO or just general LTO enabled might add a synchronization point, and that makes it a little kind of funky. But that's where, but anyway, so that's like one aspect. The other one is I don't think any of these are queries. I believe that like producing LLVM-IR is kind of just like ad hoc and like thrown together. Or internally it uses queries everywhere, but I mean like to produce the IR, but I'm relatively certain that the actual production of the CGU, like the LLVM stuff, is not part of the query system.
Oh, okay. That sounds plausible.
Not to say it couldn't be, but
I remember we talked about schemes for making it, but maybe they didn't make sense. I don't remember.
Yeah, I'm not sure any of those actually came into existence. Like I know, because queries, they always cache their results unconditionally, right? Like just in memory.
Right.
Yeah,
I mean the result.
Want to do that with.
Yeah, that's kind of why I was bringing this up. But yeah.
So yeah, I don't think we have to worry about that because it's not part of the query system today. It's more of just like you say translate and then it uses the query system to translate, but it doesn't actually use it for the LLVM stuff in the middle.
It is something where you do want it. You want to at least. I mean, it has to be integrated at least a little bit because you don't want to do it if you don't have to. But anyway, I'll look into that. It's not important. I don't think it's the high order bit for this.
And so unless there's any other, well, I mean, there's questions about the previous stuff, but there's also the job server integration, which I can talk about as well. Is that kind of the next major thing, or the last major thing, really?
Yeah, that seems important.
Any other questions on other stuff before that? All right. So we have to deal with a version of well, I'm going to go over the job server briefly just to make sure it's on video, but this might be a review for everyone. Is that okay?
No, do it.
All right.
You don't know how dumb we are. How little we know.
So parallelism is actually really difficult to deal with in build tools specifically because everything wants to use parallelism. And so one of the best examples of this is that cargo is going to spawn the number of CPUs processes. So it's going to spawn the number of CPUs Rustc instances that it actually can. But if there was no rate limiting or no sort of like limitation of how much parallelism can be done, then each of those Rustc instances would spawn another num CPU's threads. And also if this is recursive, then everyone can keep doing that. So you can very quickly, you can have the exponential blow up of the number of threads and processes on your system. And so the general idea is that in the build process, which lots of things want to do various amounts of parallelism, but there's still one build process as a whole, we want to, in general, limit parallelism on this. So we want to make sure that Cargo treats everything nicely, all the Rustcs coordinate, and especially in the Firefox's use case, Firefox has a bunch of C++ files getting built, but also a bunch of Rust code getting built. Even across that, they want limitation parallelism to make sure that you're not spawning thousands of processes. And so the solution for this is this thing called Jobserver. I believe it was pioneered by GNU Make, and it's been kind of ported to a bunch of platforms ever since. Jobserver is a name for a glorified IPC semaphore, which is where it's basically a synchronization primitive where you add in like n tokens, and you can get n tokens, but if there's not one remaining, you just block, and then you can add it back in at any time. And so the idea here is that Cargo typically creates the job server and then inherits it to these child processes. This is done via file descriptors or literally IPC semaphores on Windows. But the idea there is that so Cargo will create a token pipe with 32 tokens in it if you have a 32-core machine, and then it will take and remove tokens as it spawns processes, and then each process internally will attempt to acquire a token if it wants to run parallel work. And so there's like some weird inherent stuff about the protocol that you can kind of largely not really care about. It makes it sort of difficult for us in a few places, but every running process always has at least one token because it's the token for that process. And then it's optionally the process can acquire more after that, and then it releases them. And so the general idea, or the way that it works in the backend right now is that so our units of parallelism are extremely coarse. It's just an LLVM module, which is massive. And so whenever we get around to actually, we have a module we would like to translate. We call this request token method. I'm not going to go to Rustc, where that basically tells the job server create, please read a token, and then call some callback that you previously registered, and then it will send that token back to the coordinator thread in Rustc. And so for every single object file we get for the main thread, we're going to request a token, which will attempt to actually do a blocking read. And then once we acquire a token, we get another message, and then we say like, oh, I've got 4 tokens, I've got 3 modules, so let me just go and start executing those. And so this will dynamically manage, it'll acquire tokens, it'll spawn work as long as it has tokens, and then the, I linked it in here somewhere, I forget where, but oh yeah. So tokens are, tokens are immediately released as soon as we realize we have too many tokens. And so it's not a perfect system, like this is not nearly as quote unquote clean as GNU Make, but it's like good enough, and it's kind of fine. So there's some thrashing of the job server tokens here, but it ends up coming out in the wash and not mattering too much because the unit of parallelism is so coarse and so large. And this also means that once we acquire a token, as long as there's work to be done, we will continually hold on to that token. We're not like acquiring a token for a module and then releasing it once that module is done. It's more we just keep it as long as we have modules. We're going to keep on using it, and then as soon as we have more tokens than we have running workers, we will drop the other tokens, and then they will be released back to the system.
So let me make sure I understand. We got an internal queue of modules to translate somewhere, I guess.
Yes.
And we put them in there as they get done. Or sorry, modules to process with LLVM, to optimize, I guess.
Yes.
And as we create the LLVM IR, we stick them in this queue. Meanwhile, this like other thing is saying, someone else, I don't know who, is saying a worker thread would like to start, it needs a token, and then it just kind of pulls things from the module. So long as it has a token, it kind of gets something else from the queue of work to do, and if it ever finds that that queue is empty, it releases its token and stops.
Yes, let me actually, I will pull up the code here.
So we'll kind of get to some peak token usage, carry on until things start to finish off and then decrease.
Yes, so this is where we actually create the thing that's listening for tokens. The job server create has this into helper thread, which literally spawns a helper thread, which does the blocking reads and writes, where that helper thread is like, you send it a message of do the blocking read, and then it does the blocking read, and then it'll call this callback. And this callback is just sending on a channel saying, here we have a token. So that's sort of where we're sourcing tokens from, is you request a token, and then eventually that'll come back on the channel.
So every time you
tokens,
just that callback gets invoked whenever a new token is acquired?
yes, whenever a blocking read has successfully acquired a token, it is in this method is called. And so this just sends a like on the channel, it sends a message. And there's a bunch of stuff that I don't actually know what a lot of that stuff is. Tokens are literally stored just in a vec. As soon as we get it, like we can see, we just push the token onto the local vector and save it. And that's it. And so then we'll pump the iteration of this loop again. And the beginning part of this loop does a whole bunch of stuff. So like errors, don't worry about. And this is where this is like in every single block, and it's really complicated. We have to deal with the main thread, where like the main thread's doing crazy stuff, but largely just ignore that for the purposes of this. So we have those tokens. I'm gonna scroll back up. This is the beginning of that giant block. Here. So we say we have work, just some amount of work to do, and the amount of work we have running is less than the amount of tokens that we have. So therefore, we can spawn more work. Like we have 10 tokens, but we have 5 units. So we have 5 things in the queue, 2 units running, and 10 tokens. So we're going to spawn all that. And so this will just pop it off, increase the running account, just go actually spawn work. And then once we've actually spawned as much work as we possibly can, is where we actually truncate, saying like, oh, if we, a lot of times, like we might, like if you give us 2 modules, we'll request 2 tokens. But if we get 1 token, we finish both modules with that token, and then we get the second token, we still have to relinquish that. And like it's just, that's part of the wonky interface where it's not like as nice or clean as it otherwise might be. But it means, so sometimes we will acquire a token and then immediately release it back to the system. But in practice, I don't think this actually matters too much. But otherwise, once we get a token, we will never truncate it unless we have fewer things running that we actually currently do.
What thread is this? Is this the coordinator thread?
Yes, this thread that we're currently looking at is the coordinator thread.
And
so a lot
what
of
does
our
spawn work do? I've looked at this code before many times.
thread spawn.
Okay, so it literally
It's
starts
basically the first thing it does is, yeah, and then it sets up like a bunch of error handling for panics, and then it actually just does the go stuff. And I think like I was saying, the main thread states, or there's a lot of like handling of, is the main thread LLVMing, even though it literally never is, or is the main thread cogenning, and that sort of dance of managing that will be a lot easier once we actually have like one thread from start to finish takes the module from the beginning of translation all the way through the end to cogen, or just optimization if it's the LTO. But yeah, so do y'all have any questions about like job server or the current parallel or anything like that? All right.
Sorry, I have to deal with one thing. I'll be right back. Then maybe I do, but you can go on if you like.
So one sort of general question, how expensive is like acquiring and releasing these tokens? Is it like on the order of milliseconds or even lower?
It's a syscall, so
Yeah.
it's a read and a write on a pipe on Unix, and I don't actually know how expensive the semaphores are on Windows, but it is a syscall in some form, and so a 1 byte pipe read and a 1 byte pipe write. That's what we're paying each time.
And we only spawn the job server, like the helper thread. That's just one helper thread within.
Yes.
So it's not like constantly spawning.
Correct. And so technically, if you start Rustc, it actually immediately spawns a thread with a bigger stack. And then when you get to CodeGen, we spawn 2 threads, the coordinator thread and the job server helper thread. So those are 3 threads that we're starting unconditionally. And so, but yes, there's only one helper thread for the entire process. And I think the current parallel integration, I I don't actually know exactly how it works, but if the current parallel integration is using a helper thread, it's a different helper thread from this one. And so there might be multiple job server helper threads, which works out just fine because it's just all reading and writing on pipes, which is coordinated at the kernel level, but yeah.
Hello.
And this is sort of inherent, unfortunately. Like ideally, this would be like some non-blocking I/O loop where we can wait for a token for 5 milliseconds or whatever. But the file descriptors on Unix cannot be non-blocking, and that kind of just makes it so we can't do anything. Make is not ready for its file descriptors to be non-blocking, so we can't set them to non-blocking. So we have to do blocking I/O, which kind of forces us to make a separate thread for the job server.
So the question I wanted to ask, maybe you already discussed it, but in the loop that's calling spawn work, that's basically creating n threads
Correct.
as they come in. Are each of those threads then also pulling? Each of those threads must have a loop within them, right?
Like no, we actually spawn a thread per unit of work. We do not have a thread pool. We don't have any like reusing of threads. So that's actually, I mean, that would be, I don't think, again, it's where like the unit of parallelism is so coarse, I don't actually think it costs that much because it's a whole LLVM module. But yeah, so there's no loop internally. It just does one item and then it exits.
Okay. Okay, I see. Somehow I was misled by this performance graphs, which showed one line kind of doing multiple modules.
That was actually, that was a specific feature that I requested because this is like morally what your CPU is doing, but actually this is a special flag being passed saying, please collapse thread IDs if you can. If you don't pass that, this actually shows you a giant waterfall of just a 1 unit per thread. And that's what's literally happening. So these threads are not literally being reused. It's just in the visualization, we are quote unquote reusing the thread.
I see. That's what this crocs -- collapse thread is done, I guess.
Yes. So yeah, if you do not pass this, it's not collapsed. It's just a giant waterfall.
So what are we doing? Do you know, did you look at all at how the job server stuff is integrated into the parallel Rustc today?
I haven't taken too close of a look at that, so I'm not sure what's going on there.
I should have done, but I didn't.
So Mark was asking the cost of acquiring and releasing a job server token. And so on Unix, at least, it's a read and a write on a pipe. It's a read of 1 byte to put it back, and it's a write of it's a read of 1 byte to get it, and it's a write of 1 byte to put it back in there. So this is a very, very expensive operation for doing on like every iteration of a very tiny loop. But if you're doing LLVM, it doesn't matter at all. It's just one syscall.
I mean, what I imagine we would want, and I presume, I have to look, but I would expect this is what Lexi did. I sort of remember this in terms of like how Rayon works. It has a notion of threads going to sleep when there's no work and then waking back up, right? And they end up like blocked on a big lock, and it's something we try to avoid doing. Don't do it too lightly. It seems like that would be a time to relinquish a job server token or get one back. Like we probably wouldn't want a strategy where Rustc like acquires a bunch of tokens and never gives them back while compilation is happening. I don't know. What is the strategy we actually would want?
I'm digging this. Yeah, so you're right. I mean, assuming Rayon is doing what you were saying here, this looks like it's doing it once per thread where it's acquiring and releasing. I'm not sure. I don't know if it's calling this callback around like every work item or like every other thing.
I have to look. That's something we added for the Rustc Rayon fork. So
it does. I would suspect, I don't know, something is being called too much because I've definitely seen it super high in the profiles for when I did it a little while ago. But otherwise, you are correct in the sense that like I do think that.
Sorry, keep going. I have to have a thought.
I do think that Rustc should not hold on to threads or hold on to tokens opportunistically. It should only be holding onto a token if there's actually work to be done. Although that could be fudgeable. Like I can imagine we hold on for it for like 2 milliseconds, and if no work comes in the next 2 milliseconds, then we release it. But that sort of threshold is going to be really hard to deal with. So I do think we should try to get to a point where like we have so much parallel work flooding the system that the amount of job server stuff that we do is just very, very tiny compared to that.
So one thing I will say is that Rayon, the version of Rayon that, well, all versions of Rayon have a pretty not very good algorithm for putting threads to sleep and waking them up. It's kind of a binary algorithm, actually, where it sort of says, like, either they're all awake or they can start to go to sleep. And the point being, as long as there's work happening, it tries to keep all the threads awake. And I've been, like in the last month or two, I was hacking on an alternative one that would not be that bad, that would sort of scale up the number of threads more gracefully based on how much work there actually is. There's a few benchmarks that regress, so I haven't landed it yet. But like basically benchmarks where it turns out to be useful to have all the threads hanging around grabbing work. But that might be why you're seeing so much acquisition, that like we put in one job into the queue and suddenly we spin up all the threads and they all try to get tokens. And then, yes, they start to fall asleep. Whereas something that kind of scaled them up more appropriately might work out better. We could actually test with that fork. It wouldn't be that hard.
Yeah, I remember this profiling I did was a long time ago. Like I don't think it's substantially changed since then, but like thread creation was a big one where I think like just creating a bunch of threads was high on the profile. So it sounds like this would definitely fix that. The other one I'm now thinking of is that if every thread is waiting for a job server token, then that's definitely an issue where like once a job server token re-enters the system, then it's going to cycle through every thread one at a time until the final thread is like, every thread is like, oh, I don't have anything to do, and it puts it right back in the job server. And so that sort of cycling behavior could be really bad for performance one way or another. But I haven't, I would need to look.
What do you mean by cycling? I don't understand that.
You can imagine like if you have, so I like put a unit of work into the Rayon thread pool, and therefore 32 threads will try to acquire a job server token to run that work.
Mm-hmm.
But there's only one job server token available, and so one thread gets it and does it, but then as soon as it releases it, every other thread sequentially then gets the token and releases it, gets the token, releases it, gets the token, releases it. That might be an issue, but again, it sounds like it depends a lot on the specifics of when exactly these are required. Callbacks are called, and I suspect Stoxy knows for sure. I'm not sure myself.
I could certainly see that happening. I'm skimming over. I mean, it's not too hard to look in the Rayon source, so I'm seeing where we release it right now. But it looks like we do indeed release the thread when we go to sleep, as you might expect, and then we acquire the thread when we acquire the token when we wake back up. So probably if you did do something like one unit of work gets dropped in and then that thread goes. I'm not sure when that would happen, though. That would sort of correspond to like a slow trickle of jobs, which we probably don't do. We probably have some master queue. I don't know, I have to look. Maybe not.
I think
TLDR,
there's another one.
Rayon's really poor. Like this strategy of acquiring job server tokens and Rayon's current threads strategy just don't play well together. You really want something that will scale up.
Yes, Josh was also saying that whenever Rayon starts, it immediately spawns the entire thread pool.
Right.
That may not be appropriate for the compiler.
This will be true also on my branches, just that most of those threads would go to sleep. It wouldn't be hard, so they would release the tokens back.
That was at least, I definitely saw at the very beginning of a profile, like when we have like tons of tiny crates that take just on the order of milliseconds to compile, spawning, I have a 28 core machine, so spawning 28 threads per Rustc every single time and immediately go back to sleep and die. That actually was causing a lot of CPU contention, a lot of time spent in the kernel as opposed to in the compiler.
I wonder.
And that was on Linux, where it's
fast. Probably wouldn't be hard. I hadn't thought about that as a concern, but it probably wouldn't be hard to change that. or at least not that hard to have a notion where like the Rayon waits to actually start the thread until there's a good reason.
And this is one where like, I do think we need to probably look a little bit more into what exactly is going on in the job service stuff with Rayon right now. Like a lot of this is kind of guesswork on my end, and I'm kind of like trying to see how to improve it, but I don't know for certain what's going on.
So this comes back to the question of like, do we want Rustc to have a dependency on Rayon in the first place? Which I have mixed feelings about. Though I think it's not, like this is, it's obviously bad right now with Rayon's current scheduler. If we make Rayon have a smarter scheduler, not so bad. It's obviously duplicating some work to have more than one scheduler. On the other hand, I think Rustc would probably, like if you were going to make a scheduler for Rustc, you probably don't need as much work stealing. I kind of imagine like a central queue might suffice if we're doing coarser-grained parallelism.
And I was actually curious there in terms of like, I mean, there was the idea of what if we only parallelize like top level for loops, and given Rustc's workload, that might actually get almost all the wins, like not all of it, but it might be a huge win just doing that. And that would be relatively easy to manage the job servers for because we have like one function that just does the thing. And so I would be curious if like, especially if the Rayon work would take quite a while or just be very invasive, it might be worthwhile to prototype a scheme using Rustc or just having a top level for loop that's parallelized. And that would allow us to get these things in sooner.
Yeah, I would certainly be. So that's just something we haven't actually, we've been looking at where does shared state exist, but we haven't looked, we don't have like a good list of what are all the things we try to do in parallel, right? I mean, it's not hard to acquire one. You just have to rip grep for bar editor or something, but like, we haven't looked as far as I know.
The other sort of argument for not maybe using Rayon potentially ever is that presumably Rayon's sort of goal is to achieve more parallelism than Rustc maybe wants, in the sense that I think most applications that use Rayon probably want to sort of believe that they are the only application on the system, whereas Rustc sort of wants to do the opposite in some sense.
Yeah, I'm not sure, but definitely, I feel like job server integration, I mean, I think this is a problem for Rayon in general, like, or it's just a hard problem that other applications probably hit too, but that's part of the motivation, I think, is exactly around making Rayon scheduler a little smarter to be like, well, you know, if some threads are being very slow, that's okay. We're going to scale them more appropriately. But anyway, yeah, I don't know. I don't think it had, the main reason to use Rayon, I think, would be if we anticipate like that in the future we might want to write parallel iterators, like fine-grained parallelism throughout the compiler. Then, and it's not like we can't change.
I would be curious to see a perf run. I mean, imagining ideal code, like rip out all job server stuff, run a perf run per crate, so no job server overhead, just what we currently have, but then also rip out what we currently have and make what only parallel the top level. I would be curious to see the time comparisons between those two. I don't actually know, like, I'm not sure if we're losing a lot of opportunities for parallelism in the current compiler if we only parallelize top level loops.
My current, so looking just with a quick grep, of course, it's too bad Zoxy's not here. I'm sure he has the most up-to-date information on this, but I see that we are doing the collector. So that was the thing that you said can't be parallelized, that we are indeed parallelizing. That is to say, when we basically enumerate the full set of things we might need to put into any codegen unit anywhere, we do that walk in parallel today, which is kind of cool. And also something in the lint processing. It looks like we do each module, we lint each module in parallel. That's kind of a top level loop though.
But those are huge. Like both of those are significant portions. I mean, not the predominant portion, but definitely big loops that are happening in the compiler.
Right, and it looks like we do. These are all the here ID validation does some. They're not necessarily all queries right now. and some of them might not easily be convertible into queries, but they are fairly high-level loops that I see.
So is there anything along, like, I think at one point we were like, the type checking pass is like query type check, and you'd have one query, but the loop is all happening like internally, like, or like the parallelism comes from like the tree-like structure where I don't really know how that would work, but that doesn't really show up anywhere. It's mostly parallelism through for loops.
Yeah, because by the time like type check runs, for example, it doesn't have a tree. We've already flattened it essentially into a list of things to be type checked. That is happening. We are type checking in parallel. I can't quite find it right now, but through some call operator.
Also have some sort of lower level, in some sense, parallelism. If you look for the parallel macro, which just runs like blocks in parallel. So
okay, I see. I was overlooking that. Yeah,
there's. And that has a bunch of sort of smaller things.
Right. Yeah, so we'll do things like look for the entry point, look for the plugin registrar, look for the derived registrar, all in parallel.
It does look like most of it is high level enough that like it's either a for loop or the equivalent of a for loop, so we could probably
the parallel macro would be. Yeah, it seems this is kind of what we expect, that there's plenty of available parallelism at a high level at the moment. Well, so if we just turned off the job server, what would you expect that experiment to tell you? Are you thinking of compiling a single crate? Like without the single crate, the job server is irrelevant.
Yeah, I would want to see the single crate job server performance through perf, just to see what the overhead, if we have excessive amount of overhead, just getting and acquiring tokens by accident. I don't think we could ever land it, but it would be also interesting to see kind of the first 5 seconds of a compilation and how much of it is saved. Like, I know when I tested it on cargo, and like during the first 5 seconds, everything was like grinding to a halt versus like flying through crates. And so profiling that with and without the job server would be kind of a way just to see how bad the job server integration is, or how much of a cost it is right now. Because the other alternative is, the other thing that could be costly is the spawning threads, where every single tiny Rustc instance spawns 64 threads or 28 threads locally for me.
Okay, so we're trying to figure out how much are we costing. Oh, okay, so that's actually pretty interesting, because when we said we were talking about -J1 overhead, and we kind of said something about percentages, so that we looked for like absolute noticeable values. But what you're saying is, if you have some tiny compilation, like relatively small Hello World style small crates, and there's a large number of them, then even if they individually are not very expensive, it adds up over the course of a cargo run. So we want to pay attention to like small time, absolute or small compilations, even if they don't look individually like much.
And like, honestly, I'm not talking about 5-10%. I'm talking like, I typed cargo build on stable and it like screamed through the first 30 crates on cargo. And then I typed cargo build with nightly, just like running full parallelism. And it took like 30 seconds to get to the first 30 crates. Like, it was just insanely slow. And I was like, so I'm talking like many orders of magnitude slower. Like but then once I got the cargo, it was a hell of a lot faster. And so that's like, it's something to keep an eye on. I'm not really sure. I don't know of a great way to measure that in a like a repeatable fashion, like throw on perf or something like that. It's more of just like running it locally.
Whole system perf, yeah.
Or like insight. It's inherently a very difficult thing to measure an entire cargo build, because you don't care about instructions at that point, you only care about time, and there's so many variables that like getting any precise amount of time there is really difficult, or getting a steady measurement that's very clean and not noisy over time. And so, yeah. That's what I'm not talking about. So it's not the 5-10% small wins here and there. It's more of like you should be able to download a parallel compiler, turn on parallelism, and then type cargo build in a big project, and it should feel faster. it should not get really slow and then speed up towards the end of the compilation.
And one thing that I kind of want to ask, do we think that it's viable that if we have sufficient parallelism in the compiler, that sort of the long-term future is maybe we say cargo is no longer sort of J16 and it only spawns 5 Cs at a time, with the idea of being like it's more advantageous for Rustc internally to parallelize, or is that not really something we would expect to be interesting?
I hadn't thought about that. I would naively say that cargo will always be better at parallelism because it's just so simple. It's just processes, and there's a guarantee to be parallel and a guarantee to saturate as much as it can. And so, like, it's a question of like, if cargo can spawn a process, should it not? Because Rustc might do a better job of keeping those cores busy. And I would say, like, I feel like architecturally probably not, because like
I think
that
you want to.
process.
I just think you want to prefer the coarsest grain parallelism you can most of the time. Like,
yeah, what I was thinking about was that sort of when you get, especially towards the end of a crate graph, if like cargo is spawning dependencies still to an extent, you get this situation where even though you have a parallel compiler, you're essentially compiling all single-threaded, except you're paying the cost of locks for those first, 30, 40 crates, because they're so small that you always have 16 or 28 or however many Rustcs. Like you can always spawn more.
Well,
So you're paying the cost of locks, but you're not getting anything out of it because you can't acquire more than one token.
that's what I think that we could do a lot of work on, where I suspect that the overhead from like dealing with the synchronization of the job server, we can get pretty small, or we should be able to get pretty small. And if we can't, that's something to figure out later. But like with inherent tiny fine-grained Rayon parallelism, that might be really difficult, like unless these job server, the schedule improvements pan out. But like I can easily see that like for type checking, we could like spawn a thread to acquire a token and then like do the other half of the crate with that second thread. Like that's relatively easy to add up and would have a very low impact on the synchronization.
I'm not saying like job server synchronization. I'm saying like the compiler using locks imposes a cost if the first half of the crate graph is single threaded by virtue of just, you're limited by how many cores you have. Those locks, you're essentially always paying the single threaded cost.
Yes.
you could imagine.
I'm not really.
I mean, I think what you're saying, Mark, if I understand, is like in the beginning, there's a lot of parallelism available in the form of crates. So those crates effectively get only one job server token each, we know. Therefore, they will never get any benefit from their locks. That seems correct, but we need, yeah, I mean, one question is how low we can get the overhead, and the other question is like, I guess in the, dear God, in the most extreme version, we might have 2 versions of Rustc. The cargo sort of says like, this is looking pretty, it doesn't look like you're going to get any threads out of this, but I feel like we probably won't. Like, I think the gain we get from the end hopefully outweighs that cost. That's the bet, I guess. But the long tail is worse.
That has been my experience, where the lion's share of the compilation is spent on large crates taking 1 core at a time.
If I were to try to take that Rayon branch that is less eager about starting threads, or it'll still start the threads, but that is less eager about like scaling, waking them from sleep, and produce like a Rustc branch, how hard would it be to get some like measurements out of it? What kind of measurements would we want to get? I want to leave this call, which I think we should end, but with like, there's some measurements to make, and I feel like I don't quite know yet what you had in mind. But that seems like at least one of the scenarios to investigate.
An easy one is perf, single crate performance, make sure it doesn't regress and see if it actually improves. Another one is that given that branch, we would produce like alt compilers and just test the alt compiler for the previous commit, but single threaded, and take that to build project and see what happens. Like I'm expecting cargo to like, I guess, like I want to see the load average for a compilation to be almost at the number of cores for almost the entire time. Like that should be what we're seeing. And like for also like not just kernel stuff, but user stuff. Like that's what I would. It's more difficult to measure. It's more subjective. I mean, you could still put numbers to it, but that's what I would expect. Is like take it around to a couple of projects, build from scratch, and just see how it fares.
Okay, I'm thinking about how, like, I have to go revisit. I mean, one of the challenges here, we don't really know how much, like in a way, Rayon is kind of what we want in the sense that work stealing is reasonably well designed for these cases where you don't really know how much help the other threads are going to be, which is exactly what we have going on here. Though I guess just having a central queue and pulling jobs from them would work too, as long as it's flat. But we do things like, like Rayon will do things like divide the work in chunks that are like getting smaller, such that if it looks like you're on your own for this loop, because no one's picked up, you finished a chunk and nobody picked up any of that work from you, then you go on and you don't bother to do further subdivisions and stuff like that. So you get a lot less queuing overhead. Like just from pushing into a global queue, you don't push n things, you push log n things, stuff like that, which pays off and might be like we probably want to do the same kind of things actually. But okay.
I think some of this also is I might just want to dedicate some time to just investigating this, like getting a good story. Like we did this for ThinLTO when we turned it on because there was some surprising regressions and we ended up digging in and being like, oh, yep, these are the cases it's going to regress on. And so it might just require a lot of in-depth investigation. So like, and like, I think we're still very vague about what the cost of the job server is and where exactly the problem is, or like what exactly the problem with Rayon is. And so we're kind of hoping that this fancy new scheduler will fix everything. But once we have something concrete to work with, we can just go and investigate and like do a really in-depth analysis of trying to figure out what's going on there.
All right, sounds good. Thanks, Alex, for all this background.
Of course.
I guess we'll end the meeting. Anybody else have anything else to add?
One sort of note I can make is that I've been thinking and looking at adding the cargo-z timing graphs to perf, because we always build like the whole crate from scratch, and those graphs seem useful, and they might not be entirely precise and they probably have high variance, but seems like that could be helpful here as well, because it'll give us some insight into overall CPU usage with varying compilers relatively easily.
Neat. That's great. All right. See y'all later. We'll discuss a little bit offline, I guess.
Yeah. See ya.